Assalamu alaikum ji. This is Dr. Mohammad Numan Islam, and we are having a course of numerical methods. This is lecture number 5. Just a little recap from the previous courses, uh, from, from the previous lectures. So what we are doing actually is we started a first topic, which is the solution of the one variable equation. In this course, whenever we say a solution, so it is an approximate one. Okay, so we started with the first method, that was the bisection method, and after the revision of some mathematical preliminaries, we started the bisection method, and we did the working of the bisection method on one of the examples, and we have developed a pseudocode in the last lecture for the bisection method. Okay, if I just write in quickly what was that. So uh, so we have inputs, which is a function, interval values, and tolerance. We have an output, which will be a solution, let me call the solution P, up to the accuracy, which we call the tolerance. Okay, and what was the process? Process was, first we did the midpoint, find the midpoint of the interval. Okay, and then we apply one of the condition, which is a stopping criteria, that um, the absolute value at the central point, okay, if it is greater than tolerance, then we need to look for the solution. Okay, this is a stopping criteria, is actually the absolute value of the function at point P should be less than tolerance. If it is less than tolerance, we got a solution, and if it is greater than or equal to tolerance, we need to find a solution. And how we find a solution? We do the root bracketing. What is the root bracketing? There are two subintervals. So there is subinterval I1, there is subinterval I2. So out of the I1 and I2, we have to choose one subinterval. So how we choose that? We will be using the condition, which will be this: if the solution lies between B and P, then move A, otherwise move B. Okay, and then we did the, um, let's say this is the end of this statement, and then we do the half again, and there is the end of this while loop. Once we get out from this while loop, we will have a solution that will be our output. Okay, so that is the pseudocode that we have developed in the last lecture, and we will try to implement on the MATLAB in the coming up lectures. Once we started the basics of the MATLAB, then we will be trying to put what is the syntax available to put this pseudocode. Okay, so that was the last lecture in which we have developed this algorithm actually. So now we know about the bisection method, what bisection method is, how we know the process of the bisection method, and we know the pseudocode of the bisection method. I already told you that we can improvise it um, in the programming language. Okay, so today there is the topic. We'll starting in this lecture. We'll be going to the two topics. One is the estimation of how many uh, times we need to run a bisection method to get to a certain accuracy. Okay, so for example, if let me write an example first, and I'll be coming over here. For example, uh, if I write over here a question which is estimate maximum number of iterations bisection method required to reach an accuracy of 10 raised power minus 3 for solution of x minus cos x equals to 0 on this interval 0 to 1. So, what is actually the benefit of um, this actually topic is that we're going to cover is that before we start a problem, we will know that how many times we have to run a bisection method. Okay, so we can estimate that. So that will be our first topic that we're going to do in this lecture, and the second will be the second method that we're going to learn to find the solution of the one variable equation. That will be a fixed point method. So we'll be starting another method in this lecture too. Okay, so let's just come to the topic one of this lecture, which is the estimation of the maximum number of iterations required to reach a certain accuracy using the bisection method. So, so we have a theorem. We have a result over here. It says, let me write a result. Let f is a continuous function on subinterval with f of a, f of b less than 0. Anyone, just a recall from the previous lectures, if these condition holds, then we are sure that the solution lies over where? In the interval. Okay. So these are the two conditions that actually make sure that the solution lies between the interval a and b of this equation. When I say a solution, it means a point where f becomes 0. Okay. Uh, what is f? F is this, for example, x minus cos x. Okay. And what is a b? It is this interval. If you try to relate with an example. So uh, if these two conditions hold, we are sure that the solution lies in that interval. So the bisection method will generate a sequence anyone what this sequence is it a sequence of midpoints, because these pi's are actually the midpoints of the interval we will choose. Okay, so this is also called a sequence of midpoints. Okay, so the bisection method will generate a sequence uh, towards a solution of f of x equals to 0. Let us call that solution as p. So p is a point where f of p is 0. Okay, so this sequence is going toward this point. Okay, such that pn minus p is less than equals to p minus a divided by 2 raised power n. Okay, so we have an inequality over here. Let's try to first understand what uh, the numbers the we have, or the variables we have. So Pn is actually a sequence. P is a point where function is what? It is 0. And since, as we already discussed a lot in this lecture, in this course, that we will not be able to find this exactly if it is an irrational number. Okay, so we will be trying to approximate a solution. So Pn is actually a point um, which is going towards a point P. Pn is a sequence which is going towards a point P. So Can I call this Pn minus P as the error? It's also an error, no? If P is the exact value and Pn is the approximation, then obviously the difference between the two is the error, okay? Or deviation from P, okay? It is the deviation from P. And by the way, what is A and B? They are the endpoints of an interval. What is N? N is a point where we have to stop to get a certain accuracy, okay? Uh, can I also call this as that is the accuracy actually I wanted to achieve? For example, if the answer of this value is uh, 10 raised power minus 3, what does it mean? It means the deviation of P and Pn is this much, okay? So obviously that deviation defined the tolerance or accuracy that we wanted to achieve. For example, if I wanted a 0 up to 2 decimal places, obviously this difference will tell me if I get near to that solution or not, okay? So this is also, you can call it as, for example, in a problem that is over there, if you read the statement, it says estimate the maximum number of iteration bisection method required to reach an accuracy of this, because in every question you will be asked to reach an accuracy of a certain level, okay? So let's try to use this result to estimate the number of iterations bisection method required to reach an accuracy of 10 to the power minus 3, okay? So if I try to now use this inequality, let's try to use this inequality. It says Pn minus P. So let me rewrite it. Pn minus P is less than equals to B minus A divided by 2 raised to the power n. What is Pn minus P in this case? It is 10 raised to the power minus 3, okay? So it is 10 raised to the power minus 3 less than equals to, what is B and A? They are actually the endpoint of an interval. So B is 1 and A is 0. So 1 minus 0 divided by 2 raised to the power n, okay? So if I just rearrange this into a form, it will be 2 raised to the power n less than 10 raised to the power 3, okay? So and then if you apply a log on the both sides, uh, log is a function that does not affect the inequality. If a number is less than the another number, then the log of that number is also. So if A is less than B, log of A will also be less than log of B. So there will be no effect on the inequality, okay? So if I apply the log of base 10, let's say on the both sides, we have log of base 10. Let me use a space. So if I'm coming from here to this point, we have n log 2 is less than equals to 3, okay? Because when 3 will come over here, we only left with this thing. This is 1, okay? So it means, what is n? N is less than equals to 3 divided by log of 2, okay? Let's try to calculate this, what the number is. 3 divided by log 2. So we got 9.96. Okay, what this n is? This n is actually a number which is representing the how many times we have run bisection method. This n is a point where I have to stop that sequence because I have to use a finite many terms. Okay, I have to stop that sequence. I have to stop the working of the bisection method until I reach the accuracy uh, of 10 to the power minus 3 or whatever mentioned in particular problem. So it means n is the number of iterations that I have to run. Okay, so it should be a positive integer. Either I have to run one time, two time, three time, four time, five time. It can't be any non-integer value. It can't be 9.96. Okay, so it means you have to whenever the number come, you have to come uh, to the highest near integer. Okay, that is also called the ceiling of a number. Okay, if you take a ceiling of any number, it will be the highest nearest integer, highest nearest integer. Okay, so n will be approximately what it is 10. So now let's if you try to answer the question, it says estimate the maximum number of iteration the bisection method required to reach an accuracy of 10 to the power minus 3. Okay, so what is that? 10. So I'll write bisection method. BM is a short that I'm going to use for the bisection method. Requires maximum to reach an accuracy of 10 to the power minus 3 on the interval 0 to 1 for this particular question. Okay, so what is the benefit of this theorem can be? So the first thing is when we start a problem, we will know how many times maximum I have to run the bisection method. So if I know this information, so what is the benefit in terms of the programming or of the pseudocode? Very good. So it means we can also apply, rather than a while loop, we can also apply a for loop, because we know that that many times we have to run this process. If we know that information, it means we can also use a for loop, because in for loop we can only run up to the number of that is predefined. We have to know that that many times we need to do the process. Okay, so it means the we can also apply the for loop. Okay, but to apply a for loop, obviously we have to run this manually with our hands. We can also use, by the way, programming to estimate this number. Okay, we can also do that. Okay, so once we do that, then we can also use a for loop. Otherwise, the while loop is always an option. Okay, okay, Ji. So this is for the estimation of the computation that is required to reach a certain accuracy. Now coming towards a last thing about the bisection method, and then we'll be moving, which is um, benefits oblique drawbacks. What are the benefits of the bisection method, and what are the drawbacks of the bisection method um, um, that is possible, that is available to us? Okay, so we need to discuss that. One very strong benefit is uh, if this condition holds, that we say that, for example, when we start a problem, we say that it should be a continuous function and the endpoint should be different in signs. Okay, if this condition holds, uh, it always converges to solution. It always converges to solution, and it is a very big thing. It's always convergent. Okay, it is not a divergent sequence. It always generate a convergent sequence. Okay. Okay. What is a drawback? It's a very, very, very big benefit, by the way. Okay, we will see in the follow-up topics that this liberty will not be able to get in any other method. Okay, so under so liberal conditions. Okay, so a drawback is I'll try to explain the drawback using a pictorial view. Okay, so let's say there is an interval a and b, and the solution lies between this interval. And for example, this is the central point. Okay, and for example, our solution lies here. So this is the point P. This is the solution of actually our problem. Okay, so if I try to use a bisection method, it will just calculate the midpoint, and it will say, okay, this is not the solution up to the given accuracy, for example. Okay, so then it will obviously discard this portion and it will come into this subinterval. And again, it will do a midpoint at this point. Now you see, there is a first midpoint P1 of the sequence, and then we got a second midpoint. Okay. Then we will have a third midpoint. Then we'll have a fourth midpoint. For example, this is the fifth one, and this is the sixth one. Okay. So if I just write over here, third, fourth, fifth, and sixth, we'll be doing more iterations hopefully too. But what you see in common between P1 and P6, roughly speaking, is that they are as near, so P1 is as near to P as the P6 is. Okay, but we have to do a lot of working to get to the same point where we were initially at. Okay, so now from here it will go near to the point P. Okay, but it has computed a lot of information that is not required actually when we try to think in terms of a computation, or if we try to think wisely. If it is that near to the solution and it has identified that the solution is that much near, how are we going to identify the function value at P1 would be near a value zero point 0 something. Okay, and the P6 will again be like this. Okay, so you will see the function value at P2, P3, and P4 will be much away as compared to the function value at P1. So that's how the thing is, the bisection method go near a solution, but it does not care that it is near a solution. It just take a midpoint of the subinterval we are in. Okay, it does not take into account that I am near a solution, so I should look in this vicinity. It does not do that. If you just see the pseudocode of the bisection method, it just say, just decide the is midpoint is a solution. If it is not a solution, decide a subinterval, then do the midpoint. Okay, this is the working of the bisection method. It does not take into account that I am that much near to the solution, so I should look into this region. Okay, so it does not take into account this observation. This is the drawback of the bisection method. But ultimately, you'll see it comes near a solution. Okay, but you will not see such traits in any other method that we're going to learn. Once they are away from the method, then they'll just try to diverge. Okay, so so this is a drawback that the bisection method has, and we'll try to see how can we address this drawback into the methods we're going to learn, um, uh, possibly the uh, um, fixed point method that we will learn today. But more importantly, we'll be seeing that answer into the method when we are looking to the Newton's method. You will able to understand the uh, the drawback is being translated into a thing which is in combination would be very good in terms of a solution, finding a solution quickly. Okay, so we'll be addressing this into that lecture. Okay, so this is a one issue with the bisection method, that it takes a lot of computation at times. Okay, so you can write over here, it takes a lot of computation, okay, at times. Okay, we are going to the second method under our topic number one. What our topic number one is, approximate solution of one variable equation. So this is our topic that we are trying to do, and the first method we did is the bisection method. Now this is the second method, it's called a fixed point method. So first try to understand what is a fixed point, and then we go towards the finding the procedure of the fixed point method. So consider a function, let's say. So as an example, let's say x square minus 2. Okay. So if I plug 2 as an input, if I plug 2 as an input, you'll see what is the answer. What is the answer? 2. So input is same as output. Okay. So whatever you're plugging in, you'll be getting the same result. Okay. So the input is same as output. Okay. So for example, if I have function g of x, okay, and if I plug a value p, so the answer is p, it means p is a fixed point of this function. So the input at the points where the function is giving the same output as the input will be the fixed point of that function. Okay, so in this example, what is a fixed point? 2 is graphically speaking, for example, if this is g of x, for example, this is g of any graph of g of x, then there is a curve which is y is equals to x, which will be crossing this g of x, because this is the point where g of x is same as x, g of p is same as p. Okay, so uh, graphically speaking, two curves are intersecting actually, and intersecting at a point. What are the two curves? One of the curve is g of x, other is y is equals to x, because if they are intersecting at this point, what is the value? G of x will be same as x. Okay, so geometrically this is happening, and mathematically we try to write generally as this. Okay, this is the fixed point of a function. Okay, let's try to see how it can help us in finding a solution of an equation. For that, let me write an equation which is x squared minus x minus 2 equals to 0. So let's say this is the equation I've just written. Okay, Let's take this example. And if I just try to write, I can rewrite this equation as x squared minus 2 is same as x. Okay, so I can rewrite this equation as this. Okay, so try to understand that this is f of x equals to 0, equation we have, and let's say this is called g of x is same as x. What is this? This is g of x. What is a fixed point of this function? We just did 2 is a is it 2 is a fixed point. 2 is a fixed point of this function. So if I plug g of 2, it says 2 square minus 2, the answer is 2. So in other words, 2 is a point where the input is same as output of g of x square minus 2. Okay, so let me now write 2 is a fixed point of g of x, which is x square minus 2, and it is a solution of f of x, which is x square minus x minus 2 equals to 0. Okay, so if I use this 2 value into this equation, so it will say 2 square minus 2 minus 2, so it will be 0. So in other words, a fixed point of a certain function is a solution of a certain equation. Okay, so and they are connected. How they are connected? So from representation f of x equals to 0, I have a representation of g of x equals to x. Okay, so if this is a representation made from this equation, okay, then the fixed point of g will be a solution of equation f. I have not um, derived this g of x from any other equation, but specifically from f of x equals to 0. Okay, so you can also argue that, for example, this is the option 1. You can also say that might be, if this is the value of f of x equals to 0, I can also write x squared x plus 2, and let's take a square root on the both sides. If I take the square root on the both sides, it's x is equals to plus minus x plus 2. Okay, now if I try to relate with the generic form, I can say this is the first g1. I can also have g2, which is positive square root 2. I can also have g3, which is negative square root 2. So from the given equation, if I just have to make any a scenario which looks like this, okay, I can make number of scenarios. Okay, so then I need to find a fixed point of this function. I need to find a fixed point of this function. If I find a fixed point of any function that is derived from f of x equals to 0 in such a way, then it will be a solution of that equation. Okay, so they are related in this particular manner. Okay, now let's try to understand one thing, which is what is the working of fixed point method, how it works. Okay, then I'll come to the problem that we just arise, that we can have number of options of g, representation of g of x, because once we have a number of g of x, why I'm saying it's a problem or it's a point to discuss, because then we need to decide which one is a good one, which representation is a better representation, better in terms that it will take us towards a solution. Um, we'll come to that point, but let's try to revisit the same example that we're doing. Um, use fixed point method. So I'm using the abbreviation uh, to approximate solution of um, x minus cos x equals to 0 on this interval with, let's say, accuracy of 10 to the power minus 3. Okay, so we'll try to develop the method through the example. Okay, what is a fixed point method? We'll try to generate it from the example given. Okay, so before I go to the choice of g of x, let me just write over here. I'm just imposing a thing which is g of x is same as cos x. Okay, you can see, by the way, it's a natural choice that comes from here. So this is f of x equals to 0, and I have to write in a form x is equals to g of x. So I can write x is equals to cos x, and this is actually the choice of g of x. Okay, so at this point, our motive is try to understand what is a fixed point method. Okay, try to develop its generic form. So uh, so this is the interval where I need to find a solution of f of x. Same will be the interval where I'll try to find a fixed point, because fixed point is same as the solution of a certain equation. Okay, so the interval is not going to change, it's the same. Okay, so uh, let's say for example, I made a guess. Okay, so I'm guessing that uh, x naught equals to 0 uh, might be fixed point of this g of x, which is cos x. It might be a fixed point. So I'm not starting my uh, uh, solution from a guess which is very wise, or it's come from a very wise way. Okay, I'm just picking one end of an interval to say might be it is a fixed point. Okay, so there is no hard rule that I'm going to put over here. Okay, so I'm saying might be this is a solution. Okay, so might be this is a fixed point. So we need to check, is it a fixed point or not? Okay, let's try to check it from plugging this value into g of x. Okay, so g of x naught will be what? Cos x naught. What is the value of x naught? It's cos 0. So what is an answer? 1. Okay, so what is an input? What is an output? So let me call, because they are not same, they are not same, let me call it x1. Because they are not same, obviously they are different numbers. So let x naught is an initial value. Then if the output is not same as x naught, let me call it some other number, and let me call it as x1. Okay, so and anyone, x1 minus x naught, what is this? This is an input, this is an output. A point will be a fixed point if input is same as output. So if it is not same, so this is an error. This is a deviation from input of the output. This is a deviation. Okay, so and uh, the acceptable range of the deviation is what? The accuracy. I wanted a solution up to 10 raised power minus 3. So I want a fixed point up to 10 raised power minus. If a number matches the another number by these decimal places, so that will be okay for me. Okay, so I want this number to be less than 10 raised power minus 3. I want this number to be less than. I want my input and output to be matched by the accuracy I wanted. Okay. So if the number is less than 10 raised power minus 3, it means the input and output matches by these decimal places. Okay. So this is, and by the way, the value is 1. So 1 is less than, 1 is not less than 10 raised power minus 3. So I need to keep, continue finding a solution. 1 is not obviously less than this value. So now what I'm going to do, I'm going to find g of x1. Okay, because I have used the value 0, which was my initial guess. Now the updated value that I got is 1, which is an x1. Okay, so cos x1 is the cos 1. Okay, if I use the calculator, and I have to use which mode of the calculator? Which mode? Radians or degrees? Radians. Okay, use the radians mode, please. Okay, so it's 0.5403. I'm just writing up to 6 decimal places just to show. So I have round off up to 6 decimal. Let me write over here an approximate. Okay, so just to have a bigger view of what is happening. Okay, so let me call this as x2. What is x2 minus x1? This is an input and this is an output. Okay, and this is the deviation uh, um, from input to the output. Okay, so this is the deviation. By the way, if you just subtract this number from 1, which is an input, so it is in absolute term is 0.459 8, sorry, 9798, for example, 246. Okay, and it is not less than 10 raised power minus 3. So if it is not less than, then I have to carry the updated output, uh, g of x2. Let's calculate g of x2. I'll call this at x3. So what I can do is actually, I can just in calculator, I can write cos of answer. Cause of answer. You can use a keyword answer on the on your calculators while exam, because this is the number that your calculator is showing at this time, which is stored in answer. Okay, so you can just write cause of answer. So if you have calculators, by the way, you can just, if you just write cause of answer, it means you're getting the value which is 0.857553. Okay, so you see a deviation which is, let me write over here, it's x3 minus x2. This is the deviation we have. Okay, so 9698. So the value is 0.397855, which is not less than 10 raised power minus 3. Okay, so you can just keep calculating x4. It will be g of x3. Anyone? What is uh, xn? G of xn minus 1. And what will be the criteria to check either we need to stop or not? Xn minus 1 is an input, xn is an output. Is it less than the tolerance? If it is less than tolerance, I need to stop. Okay, what is this? This is a fixed point method. Exactly. So so we have a suggestion that whenever you, until you don't find a solution, you keep doing it. So the good news is using a calculator while doing this method, so it is very easy to do that because you just need to press the equal sign. So you'll be at the next iteration because you're using a cause of answer. Okay, so so let me just start from the problem again. I'm just using cause of 0 because we start a problem from cause of 0. Okay, so I get an answer 1. Then if you have calculators, you can also go like this, and then you can just write cause of answer. So you will see that your calculator will start fixing a number at the first decimal, which is zero point 0.7. We know the solution of this equation when we do the bisection method. It was 0.73 something. Okay, so how many times you're pressing the equal sign will be the how many times you are doing the iteration of fixed point method. That is the value of n. Okay, so you will see that at this stage the error was what? 1. The magnitude of the error was 1. Then the magnitude error was reduced to 0.45. Then the magnitude is reduced to 0.39. It means the deviation of the input and the output is becoming smaller. Okay, so we are going towards the solution. Okay, so we're going toward the solution. Well, and you will see on your calculator screen uh, that the first index will be fixed, then the second index will be fixed, then the third index will be fixed. It means if the first index is fixed, you get a solution. The first decimal if matches, so if you subtract those numbers, you're getting a 0 up to 1 decimal place. Okay, so if two indices are fixed, you're getting a solution up to second decimal place. So that's how you becoming near to the solution until the machine which is on your hand uh, have its limitation up to 10 or 12 decimal places. Okay, so that will be a point where we will be going to stop. So by the way, this is the bisection. This is the fixed point method. Okay, so the iterative scheme of the fixed point method is the one I just highlighted. Okay, uh, I need your guidance in just writing 2 3 things, which is um, can anybody? Let's try to do it together. Let's try to write a pseudocode of fixed point method. Okay. So what is the inputs? So I need a choice of g of x, and what else input is? X naught. And what x naught? A good word for x naught is initial guess. So I need an initial guess. Okay, it does not require an interval. Bisection method requires an interval. It does not require an interval. It requires 1 point, one real number. So I need initial guess. Okay, let me call that as x naught. Okay, and also I need an accuracy by which you want a solution. Okay, these are the inputs. Um, what is an output? Output will be xi such that the or let me write xn such that xn minus 1 will be less than 12. Xn minus 1. By the way, if you look at this scheme that we have developed, if I plug an input and the output is same as the input up to the certain decimal places, so input is the solution. What is a fixed point? A fixed point is a point that you're going to plug in. Okay, so that is the solution xn minus 1. So that's why I just, rather than writing xn, I just write xn minus 1. So xn minus 1 will be a solution in which this will be satisfied. Okay, so what is the process? Can we use a for loop? No, we can't use a for loop because we don't know how many iterations we need to run. Okay, so either we can just use the condition that we are using in the bisection method, or we can also use this condition. Okay, which is uh, so if this is x naught, what is x1? This is x1. Okay, what is the condition? Understand while as if, repetitive, because we have to keep repeating a thing. Okay, if x1 minus x naught, this is input, this is output. If they does not match, then I need to find a solution. If they match, I will just get out of the loop and I'll write x naught is a solution. Okay, if x naught is not a solution, that is it is greater than or equal to tolerance, then I have to do what? I have to calculate I don't want to use so many numbers. I'm just using x naught and x1. So if x naught is not a solution, then uh, let's replace the x naught with the updated value. So now x naught will have an updated value, and on the updated value, whatever the g value will be, it will be assigned to x1. So x naught is an input, and x naught become an out, x1 become an output. Okay, because obviously there are restrictions of whenever you're writing on the programming language on some softwares. So it's just a swapping. I'm trying to just swap the roles just to be a good programmer while using the less variables. Okay, so you'll see if x naught, so this is an updated value, it will go over there and it will check is it a solution. If it is not a solution, uh, then it will say okay, just assign x naught and x1 value, okay, and just try to calculate the new one. Okay, so that is just a quick pseudocode that we can develop the bisection method. So we are able to develop the pseudocode simply. So it's not a big in terms of a problem uh, while we're trying to develop more methods in terms of pseudocode. Okay. So just trying to now wrap up what we have done in this lecture. We started with the bisection method, finding the maximum number of iterations of the bisection method. Uh, the thing that we got from there is we can also apply a for loop, or we can actually, before starting a problem, we have an estimate that that much amount of work or computation we need to do to get to this accuracy. Okay, so that is the information that we can have. Then we move to the second topic in this lecture, which was the fixed point method. So we learn about the procedure. We develop a general form of the fixed point method. It's also called fixed point iterative scheme. Okay, this is also a word for that. And then we have just solve a problem and we develop a pseudocode. Okay, so in the coming up lecture, we'll be seeing what are the drawbacks of the fixed point method. Does it also, can it diverge? Okay, and what will be a good choice of g of x. So when we start the fixed point method, I have written a certain choices of g1, g2, g3 of a same equation. So what will be a good choice of g of x that will make, we will be sure that we'll get into the solution. Okay. So if you have any question from the lecture, you can ask, please. Thank you so much.